All right, so what we're going to be moving to into the next chapters are really talking about hypothesis testing. And so we'll start off with hypothesis testing with one sample. So this is really moving into inferential statistics. So the nice thing about hypothesis testing is that you can do this in any type of research discipline. So not only in health sciences, but this is used frequently in psychology, in social sciences, I think political science, and it's great that this applies across so many things. So the training you receive doing this stuff really applies to any kind of science. So really what we think about is what is a hypothesis, and this is the claim about a property of a population. So this is what we think is going to happen. Do we want to prove something in some direction, or do we want to prove some effect is happening? This is what our hypothesis is. So we state this in the positive statement saying that this is what is going to happen. So then to make this claim, we have to perform a hypothesis test, which is a standard procedure for testing a claim about a population. So what we're doing is using from our sample what we infer about that to the overall population of interest. Okay, and we've already kind of touched on this, where the significance of hypothesis testing is based on chance, right? So we've talked about this in terms of, do we see things that are very likely to happen, or are they unlikely to happen, right? So now we're changing those terms a little bit and saying things that are likely to happen are not statistically significant, but things that are very unlikely to happen by chance alone is what we'll call statistically significant. So we're just kind of changing some of our framework of what we thought about unlikely events and likely events to now statistically significant or not statistically significant events. So this is an easy example to think about. So gender choice. So for instance, if we had a product that says that you'll get the baby of the gender of choice that you'd like. So for instance, if you wanted a boy, your chances would increase to 85%, and if you wanted a girl, your chances would increase to 80%. So the experiment that we do, right, is that we're going to test whether this claim is true, right? Testing whether this hypothesis is true. So we'll follow 100 couples, and then they want to get a girl. So how many girls would we expect by chance alone? So what will we conclude about the claim if 52 girls were born, and what will we conclude if 92 girls were born? Okay, so what are things that are likely to happen, and what are things that are unlikely to happen? Okay, and this lets us test whether we observe something, whether it's observed by chance, or is it unlikely to happen, and therefore that product is effective. Okay, so now let's move into actually how to do hypothesis testing. Okay, so we'll really use 4 steps here, and this is what I want you to kind of think about in your head every time you're doing some kind of hypothesis test. So I still do this when I'm running any kind of hypothesis test. Okay, so step 1 will be stating the hypothesis, right? So what is the claim that you're trying to prove? Step 2 is setting the criteria for your decision, right? So we'll talk about this more in depth in the subsequent slides, but basically, what do we say are the values that would tell us whether something is likely or unlikely to happen? Step 3 will be to collect the data and then to compute the sample statistics, right? So for purposes of this class, we're not really going to quote unquote collect the data, right? We're just going to get it, and then we'll compute the sample statistics using known formulas. And then step 4 is to make your decision and then draw a conclusion based off what you observed from step 3. Okay, so step 1 is stating the hypothesis, right? So we have 2 opposing hypotheses, right? So we'll start with the null hypothesis first, right? So if you've taken any stats before, you've seen these terms before. But a null hypothesis is stating that there's no change, no difference, or no relationship, or no association, right? And we denote this as H naught, so the H with the 0 under it, which is there is no effect of the independent variable on the dependent variable, okay? So that the value of the parameter is equal to some claimed value. So thinking back to the example of gender choice, we would say that our null hypothesis means that the drug doesn't change our the baby's gender that we would like to have, okay? Therefore, it's not working. There's no effect of our drug on the number of girls we would have, okay? Our alternative hypothesis is therefore the opposite of the null, which is that there is a change, there is a difference, there is a relationship, there is an association. So we denote this as H1, or we can also use the term HA. Either is fine. But here we're saying that the independent variable does have an effect on the dependent variable, and the parameter has a different value than the H0 value, right? So this is saying that yes, the drug is working, right? The drug does change our percentage of girls being born. And so much like we've talked about in the previous chapters, right, we have parameters that we test for both a proportion and also for a mean, okay? So the first part of this slide is the notation for testing a proportion. So the top left corner, we see the H0 for the proportion being equal to 0.5, right? So P in the overall population is equal to 50%, right? So if we're thinking about that whole gender choice question, we'd say that if there is no effect of the drug on gender, we would assume that half the time we'd get a girl, half the time we'd get a boy, right? That means there's no effect of the drug on our gender choices. So that's why it's equal to 50%. That's our null. There's nothing happening. The alternative we write as either P being not equal to 0.5, right? That it's different from 50%. We can also write terms in it being either greater than 50% or the proportion being less than 50%. And we'll get to that later. But the difference between this is that one's called a two-tailed test and the other two are one-tailed tests where we are predicting a direction, right? One, we'd say it's different and we don't know whether it's going to be less than or greater than. And in the second two of the proportion tests, we could say that, yeah, we know for certain that it's going to at least decrease the level of that proportion, okay? So we do the same thing whether it's a proportion or a mean, but remember a mean, we have any possible values that we're interested in. So here we write that the null hypothesis is that the mean is equal to some known value, right? And then alternative hypotheses would be that they aren't equal or they're greater than or less than. Okay, so a little bit more about the null and alternative hypothesis. So we're thinking about them being mutually exclusive things, meaning that one and the other can't happen. So only either the null or the alternative event can be true. So the alternative can state that a sample is not equal to, it's greater than, or it's less than. So that's what I kind of alluded to in the previous slide. So we'll get into a little bit more detail. The not equal means that this is a non-directional hypothesis. So we call this a two-tailed significance test, right? Meaning we don't know whether the effect will be smaller than or greater than what we propose. The inverse of that is that things can either be less than or greater than, where we prove a direction, right? So it can be less than or it can be greater than. So those things are also mutually exclusive events. So we're specifying the direction of a difference. So this is a one-tailed significant test. So we call something a right-tailed when we're trying to prove whether something is greater than, or it's left-tailed if it's less than. Okay. So here's an example of null and alternative hypothesis if we're testing a mean, right? So if college students come from a population with an average IQ of a population mean of 100, our null hypothesis would state that the mean is equal to 100 and the alternative would state that it is not equal to 100. So here this is a two-tailed test, which is non-directional. We're trying to prove whether this sample of this larger population is truly equal to 100 or it's not equal to 100. Here is another example. Does prenatal exposure to alcohol affect newborn baby weight? So let's assume that the average newborn weight is 7 pounds, and we're studying a sample of newborns whose mother drank alcohol during pregnancy. So we have two hypotheses here, right? The null and alternative. The null being that the newborns with prenatal exposure to alcohol will weigh 7 pounds, right? That they're not significantly different from 7 pounds. The alternative is that the newborns with prenatal exposure to alcohol will not weigh 7 pounds, or if we'd like to write that in a directional way, is that they will weigh less than 7 pounds. So our notation is that the null, right, is the H0, is the mu is equal to 7. The alternative H1 is that the mu, or the mean, is not equal to 7, or that the mean is less than 7. So here we can choose a direction, usually because we think that prenatal exposure to alcohol would probably cause a decrease in newborn baby weight. That's probably the most likely effect of alcohol on a fetus. So that's more important to say that, yes, we want to prove that the direction is less than, right? It's not as important for us to prove that there's something that's happening that's greater than, because alcohol wouldn't work that way in a newborn. So that's why we can choose a one-tailed hypothesis in this instance. So far we've only covered step 1, right? Meaning we've stated our hypotheses. Step 2, we need to set the criteria for decision. So the data that we've collected from our sample will either support or not support the null hypothesis, right? And this is either that the sample is consistent or basically the same as what we think the null hypothesis is going to be. So then we can divide our distribution of our sample means, or the proportion that we use to estimate the normal distribution, into 2 sections. So the sample means that would be likely to be obtained, right? Meaning that middle portion of things that we think are very likely to occur. So that means that the null hypothesis is true, right? That the mean is not significantly different from what we expect it to be. And then we also divide it into things that are unlikely to be obtained, right, if the null hypothesis is also true, so that the sample means are very different from the null hypothesis that we've stated. Okay? So here's our criteria for a decision, but we've already seen, right, from the last chapter where if the null hypothesis is true, there's that middle area right in the middle of our normal distribution is that the null hypothesis is true, right? We expect most normal values to be obtained in this range of potential things, right? The 2 tails, or the extremes, is that those are less likely that the null hypothesis is true, right? That the mean is equal to some stated mean that we've set. Okay, so what we would like to do is identify results that support that null is true versus which results don't support the null. Okay. And so part of this is also setting the alpha level, right? This is where we have to define what we think are the low and the high probability areas of our null hypothesis being true. And so now we've kind of changed our term of alpha level, but we'll change it into what's called the level of significance. And we've already seen this before, right? So we're just kind of adding on to this and calling it a level of the significance instead of just an alpha, or our area of the extreme ends of the tail. So we've used the values for an alpha of 0.05. We've also used the one for 0.01, and now we're just going to add another one potentially as an option as 0.001. So the alpha of 0.05 separates the most unlikely 5% of the sample means that we've obtained, those extreme values, from the most likely values, so the 95% region in the middle. So extremely unlikely events make up the critical region, values that are inconsistent with things that we think are in the middle of the null hypothesis. So it's the same concept, is that we've set our critical values, which are the boundaries for the critical regions, those extreme unlikely things to happen if the null hypothesis was true. So our critical regions are values that would be unlikely to occur if the null hypothesis is true. And this is set depending on the alpha level that we have. So if our alpha is 0.05, we have a 5% in critical region, where we have 2.5% on each side if we assume a non-directional or a 2-tailed hypothesis, right? So the same value that we used from before, which is our z of 1.96, this is the critical value that discriminates between the bottom 2.5% of the curve as well as the top 2.5% of the curve, right? These are the values that would be unlikely to have been observed if the null hypothesis is true. Okay, so if our sample mean is way beyond what the population mean that we've collected is, we can reject the null hypothesis, right? So if we're doing that whole, let's say that IQ example where we said that the mean was 100, right, in our population. If our sample mean was, 200, that means that this sample is way different than our observed population mean of 100. Right? It makes sense, because what we're saying is most values would occur around 100 and given some standard deviation that we've collected, and then those extreme values would be way outside of the range that would be normal to occur, right? An addendum to this is what's the difference between doing a 1 versus a 2-tailed test, right? So a 1-tailed test is, or sorry, let's go with the 2-tailed test first. Our 2-tailed test, we're basically dividing our probability of the alpha level that we set to both sides. So of our 0.05, we have always divided by 2 and stacked them on both sides, right? So here we see that the probability of 0.025 is both in the shaded gray area on the left and on the right. So that's the value of 1.96 that we've used if we're doing a two-tailed test. If we're in a direction, if we choose a direction, so we would stack all of that probability all on one side. So we would look directly for the 0.05 on one side of the curve. So here we're just trying to prove that the mean of group 1 was bigger than the mean of group 2. And that's why in the crossed lines you can see that the z value is less than, meaning that it's much easier to declare something as significantly different in terms of our sample mean to our population mean if we're using a one-tailed versus a two-tailed test, right? So this value is about, and you know this is actually 1.645 versus a 1.96 because all of our probability is now put on one side of the tail instead of being divvied up into both sides of the tail. Okay, so here's just some examples that we've seen before, right? So for instance, if you have a two-tailed test with your alpha of 0.05, we're stacking it on both sides of the distribution. So now we have 0.025 on each tail. So then the z becomes 1.96. In a one-tailed test on the right hand of the column, we see that an alpha of 0.05, the 0.05 stays on either side, right? It's only on the right or it's only on the left. And that z corresponds to 1.645. And then you can see the same example for an alpha of 0.01. So make sure you're understanding what happens when you do a two-tailed versus a one-tailed distribution in a test. So a p-value, which we'll interpret, we'll get into this. So the definition for a p-value is the probability that you obtain a value by chance alone. And we'll get to that in just a couple of slides. Okay. So step 3, we've collected our data, we've computed a statistic. So then we collect our sample data, right? So we'll assume that you've all collected your data and it's done very well. And you've collected this after you've stated your hypothesis and you've set your criteria for significance. So remember that these things fall in order. So now we can compute our sample statistic, right? Whether it's a mean, whether it's a proportion, whatever else you'd like to do. But then we can compare to convert our z-score that tells us the exact location of the sample statistic relative to the population parameter that we'd like to test, right? So where does our sample statistic compare in relationship to the population value that we're trying to test, right? Is that mean that we've collected in our sample so much different than our population mean, or is it the same? And we've seen these formulas before, right? Our z-score for a proportion is just given by p hat, so our sample statistic minus the population proportion over that standard error for a proportion. And then we do the same thing for the mean. And then our last step, so step 4, will be to make a decision based off all the subsequent or previous steps that we've done. So either you decide to reject the null hypothesis, where we'd say that yes, there is a difference, there is a relationship, or there is an effect, right? Meaning that our sample mean is truly different from the population mean that we've stated as our null hypothesis. So this would mean that the z-score is in that critical region. It's beyond what we would have observed from the population mean. Or we choose to fail to reject the null hypothesis, meaning that there is no difference, there is no relationship or an effect, right? It's basically in the middle. It's in that middle 95% of the estimated sample means that we would have collected. Okay. So our final conclusion, right? We either reject or fail to reject the null hypothesis. So these are always about the null hypothesis, so that there's sufficient evidence to support the claim made by the alternative hypothesis, or there's insufficient evidence to support that the alternative hypothesis is true, okay? And an important note, which we've talked about before, is that we can never prove anything. We can't prove causality in statistics because there's always potentially room for a random error in our conclusions. Okay. So like I said, there's potentials for error, so that's why we can never make conclusive statements, right? All we can say is, yes, there's an association, but there are potentials for error when we think about whether we state whether our sample is different from the population. So there could be that you might have selected an extreme sample by chance, but really that treatment didn't have an effect, right? That the IQ isn't really different in our high school than the population. So this is called a type 1 error. The other type of error that you can have is that, yeah, the treatment did work, but the sample wasn't really different from the population mean, and this is called a type 2 error. Okay, so type 1 error occurs when the null hypothesis is rejected and it's actually true. So that means we said that something worked when in reality it doesn't really work. So the problem is that the information from the sample was misleading because our sample said, yes, it looks different from the population. But if for this omniscient being, and we think that we know everything, in reality, those things aren't truly working. So this is a serious problem because it can lead to a false report, right? Because we'd say, oh my God, this drug works, it's doing everything correctly, but in reality, it's not actually doing anything. So we're selling this drug and we claim that it works, but it's not. So this alpha level tells us the chances of committing a type 1 error, right? So when we set this alpha, this also corresponds to a type 1 error. So we're always saying that there's a 5% chance that the sample mean falls in the critical region, even if the alternative is true, right? And because of this, what we're doing is we set our type 1 error, right? Meaning we set the alpha, and then this is under our control. So this is a kind of error that we would make by random, and we'd say that there's a difference when there's not really one in reality. Okay? A type 2 error is when we fail to reject the null hypothesis, and it's actually false, right? So it is effective, but we didn't detect it when doing our test. Okay, and this is in as a serious of a problem, right? Because we're not making false conclusions about something that doesn't, if something doesn't happen and doesn't, we don't detect it, so that it doesn't really matter. Okay. So this is a good 2x2 table to look at. So it's a 2 rows, 2 columns. When there's something about the omniscient truth, right? When there's really no effect, or really there is an effect, and crossed with that is our decision, right? When we decide based off our sample, we either reject or we fail to reject the null hypothesis. So if we reject the null hypothesis and there is an effect, that's the correct decision, right? Because we said that the alternative hypothesis is compatible with our data and there is truly an effect. So yes, this is good. If we fail to reject the null hypothesis, meaning we said there's no difference between the sample to the population, and in truth, there is no effect, this is also the correct decision, right? We didn't make any statements about something because nothing is happening. And then in the red is our errors, right? A type 1 error is when we reject the null, but there really is no effect, right? We're not overstating our conclusions. And the type 2 error is when we fail to reject, but there truly is an effect, okay? When we didn't detect it in our sample, just by chance. Okay, so just some slides for y'all to review, but we'll end here with this material.